Hello and welcome. My name is Zhibin Guo and I'm an application engineer at Bettersize. It's my honor to introduce the BeNano 90 Zeta to you, the latest generation of nanoparticle size and Zeta Potential analyzer from Bettersize. This talk will be divided into 4 sessions. Firstly, 3 important concepts, particle size, Zeta Potential, and molecular weight, will be introduced briefly. Then the optical system of the BeNano 90 Zeta, including dynamic light scattering and electrophoretic light scattering, will be shown in schematic diagrams and animations. Next, a detailed explanation of features and benefits of the BeNano 90 Zeta will be given, including hardware, software, and various accessories. Lastly, I will introduce a few applications as examples using this instrument. First, let's get to know some fundamental concepts. The BeNano 90 Zeta integrates with DLS, ELS, and SLS to provide accurate measurements on particle size, Zeta potential, and molecular weight of nanoparticles respectively. You may wonder what these concepts are and why they are important. Please follow me with a walkthrough on the introduction to them now. Particle size is a physical property to indicate how small a particle is. The effective control of the particle size and size distribution of materials are very important in many fields for improving product quality, reducing energy consumption, controlling environmental pollution, and protecting human health. There are many instruments and methods for particle sizing, and DLS is one of the most widely used approaches for submicron and nanomaterials. It has advantages including fast measurement, easy operation, and good repeatability, and thereby becomes one of the principal methods for nanoparticle measurements. Vernier motion is the random motion of particles suspended in a fluid, resulting from thermal fluctuation of the solvent molecules. Due to Vernier motion, in the same time period, for bigger particles, the displacement is smaller. On the other side, for smaller particles, the particle displacement is larger. Therefore, the relationship between the diffusion coefficient and the particle size can be used to calculate the particle size of the sample through the Stokes-Einstein equation. The DLS technique utilized in the BeNano 90 Zeta can obtain the equivalent particle size through the hydrodynamic behavior of the particles. In other words, the measured particles and the equivalent spheres have the same diffusion behavior, namely Vernier motion. Particles usually carry charges on the surface in aqueous systems, surrounded by contact ions that form a firmly inner stern layer and an outer shear layer. The electric potential reaches the maximum at particle surfaces, which is called surface potential. The stern layer locates at the double layer's inner region, where ions are strongly bonded, and the electric potential measured at this layer is called stern potential. Zeta potential is the electric potential at the interface of the shear layer. Within the shear layer, all components move with particles, whereas solution environment refers to any position outside the shear layer. The sign of the zeta potential indicates whether the particles are positively or negatively charged. The value and the sign of zeta potential depend on the chemical composition on the particle surfaces, and also the environment in which particles are dissolved, such as pH, ionic strength, and formulation component. Therefore, zeta potential refers to electric potential for a specific type of particles suspended in specific solution environment. Zeta potential is a key indicator of the effectiveness of surface charges at keeping other particles apart. Measuring zeta potential enables stability comparisons between particle systems that are obtained through different environments, formulations, and engineering processes. Suspension system with higher zeta potential tends to be more stable and less likely to form aggregates, while lower zeta potential leads to flocculation, aggregation, and agglomeration of particles due to van der Waals force. Measuring zeta potential is a significant application to many industries, including chemistry, chemical engineering, pharmaceuticals, environmental protection, and food science. The molecular weight is the weight of a given molecule, which is measured in daltons. The molecular weight is a significant parameter of polymeric materials for determining the mechanical, bulk, and solution properties of materials. There are two approaches to measure particles' molecular weights in the BeNano 90 Zeta. One is the calculated molecular weight using the DLS technology, and the other is the measured molecular weight using the SLS. What's the difference, and how does the BeNano 90 Zeta obtain them? I will explain in detail in the later slides. After introducing the fundamental concepts, let's move on to the next section, the optical system of the BeNano 90 Zeta. Have you wondered how does the BeNano 90 Zeta give the size of particles? Simply put, the scattering fluctuations of particles are detected and then converted into correlation functions. Then, by using DLS algorithms, the average size based on intensity, or known as the average size, is calculated. Here the technique used is called DLS. It's a technology utilized in the BeNano 90 Zeta that measures the sizes of particles in nanometer range. In a DLS setup, a coherent laser beam illuminates the uniformly dispersed nanoparticles in the sample cell. The scattering intensity fluctuates over time due to the continuous random walk of particles undergoing Vernier motions. The APD, avalanche photodiode detector, determines the number of photons in scatter line, and the processor computes the sample autocorrelation function. The diffusion coefficient is then calculated and used to provide the average size through the Stokes-Einstein equation. Particle size measurement is performed with the DLS technology using a detector at 90 degrees. During particle size measurement, a vertically polarized laser beam illuminates the sample cells after being reflected by two mirrors. The attenuator adjusts the instant intensity of the incoming laser beam. The sample is placed in the sample holder that is capable of controlling the temperature with high precision. An APD detector aligned at 90 degrees collects the scattering of the particles and records with time. Therefore, the intensity of the scattered light detected by the photodetector fluctuates over time, as shown in the figure. If there are large particles, the Vernier motion will be slow. The scattered signal will change gradually, and the correlation will continue for a long time. However, the correlation will decay more rapidly if the particles are small, which experience fast Vernier motion. By analyzing the correlation functions, the BeNano 90 Zeta obtains diffusion coefficient and then particle size. This is how the DLS design of the BeNano 90 Zeta works. Another technology employed by the BeNano 90 Zeta is ELS, which is a light scattering technology utilized to measure the surface charges of particles suspended in a solution via Doppler shifts in scatter light. After applying an electric field to both sides of the sample cell, the charged particles dispersed in the sample suspension undergo electrophoresis movement. Due to the Doppler effect, the scattering intensity has a frequency shift compared to the instant light. The magnitude of this shift depends on the velocity of the electrophoresis movement of the particles. A detector set up at the forward direction detects and analyzes the scattered light to obtain the frequency shift and eventually particles' electrophoretic mobility. Through Henry's equation, the Zeta potential and its distribution of the particles in suspension can be obtained in the software. Zeta potential measurement of the BeNano 90 Zeta is performed with the ELS technology using a detector at 12 degrees. In a measurement, the beam splitter splits the laser beam into the main beam and the reference beam. The main beam is then reflected by two mirrors, illuminates the sample cell, and scattered by samples, while the reference beam passes through the PZT and the reflecting mirror and combines with the scatter light coming out of the sample cell at the detection angle as one beam. The APD connected with the optical fibers collects the scattering intensity of the combined beam at 12 degrees, which is further analyzed by the software to obtain the Zeta potential. You may have noticed that the electric field periodically reverses direction. This is a more sophisticated technology compared with the traditional ELS, called phase analysis light scattering. Or we can just call it pulse. It's employed to analyze the beat signals by measuring the phase shift instead of frequency shift. Pulse is able to provide more accurate results than common correlation analysis. In an ELS measurement, an alternating current is applied to the sample to alternatively change the electrophoresis directions of charged particles. Pulse detects the changes in phases of scattered light with respect to time. The slope between phase change in time is proportional to the frequency shift, and the electrophoretic mobility is proportional to the frequency shift as well, according to the equation. Then Henry's equation relates the electrophoretic mobility to zeta potential. So the BeNano 90 zeta can provide the parameters including average zeta potential, electrophoretic mobility, and conductivity. This is how the ELS design of the BeNano 90 zeta works. As I have mentioned previously, the BeNano 90 zeta can measure particles' molecular weights by both DLS and SLS techniques. Static light scattering, or SLS, measures the molecular weights of macromolecules and proteins dissolved in solutions. During the measurements, the instrument detects scattering intensities of particles in solutions at different concentrations. The software computes the Rayleigh ratios of samples at different concentrations and plots them against a concentration into a debye plot. The molecular weight and the second virial coefficient A2 are then obtained through the intercept and the slope from the linear regression of the debye plot. Another type of molecular weight provided by the BeNano 90 zeta is the calculated molecular weight. According to our knowledge, the size of a molecule is directly related to its molecular weight. With equation 1 and equation 2, it can be concluded that the molecular weight of a macromolecule is inversely proportional to its diffusion coefficient. That is, the larger its molecular weight, the slower it diffuses in the solution. Then, the molecular weight and the diffusion coefficient can be related through the equation 3, Mark-Howick equation, where kappa and alpha are the empirical constants. With known particle size, the users only need to call on kappa and alpha constants in the software to calculate the molecular weight without actual measurement. That is why we call it calculated molecular weight. Right now, we have walked through the overall optical system of the BeNano 90 zeta. To put it simply, a unique design of the multi-angle detection has been set up to detect the scattering intensity at different angles for DLS, SLS, and ELS measurements. If more technical information is required, please access our Bettersize website or YouTube channel. Besides the technical things, the truly concern is what the BeNano 90 zeta can offer you, and what are the features and benefits. As I have mentioned, the BeNano 90 zeta integrates with 3 technologies: DLS, ELS, and SLS. Through DLS, you can get the average size and polydispersity index of your sample. The size distribution can be provided based on the intensity, number, volume, and surface area. Although intensity distribution is the primary results given by DLS, the BeNano 90 zeta software offers the options for users to change the particle size to number, volume, and surface area distributions in case the result comparison between instruments or technologies is required. In the ELS measurement, the zeta potential average and its distribution of particles could be measured so as to evaluate the dispersion stability of your sample. With SLS, the BeNano 90 zeta provides users with the molecular weight and the second virial coefficient, the significant properties of polymeric materials. Apart from the principal parameters I have introduced, other measurement parameters you may need for your research, such as diffusion coefficient, interaction coefficient, and solution viscosity, are also offered by the BeNano 90 zeta. The features and benefits are divided into 3 parts in my presentation, including hardware, software, and accessories. Please note that given our time restrictions, only a few features are mentioned here, and it's strongly recommended to refer to the detailed information in the BeNano brochure, which has been released on the Bettersize website. The BeNano 90 Zeta utilizes the helium-neon laser source, which is highly stable and not affected by power supply fluctuations and temperature changes. It can generate a monochromatic and coherent laser beam for the light scattering measurement with high power, excellent stability, long life, and low maintenance cost. The APD detector, avalanche photodiode detector, is used in the BeNano 90 Zeta. The detector significantly decides the sensitivity of the instrument. APD is a more advanced detector than photomultiplier or photodiode detector because its quantum efficiency is larger than 70%, which is a huge progress compared to PNT. There's no need for high voltage power supply in the measurement, and effectively increase signal-noise ratios due to high sensitivity of the optical system. In addition, the highly precise temperature control system is built in the BeNano 90 Zeta. Temperature, an essential parameter for particle size measurement, has to be precisely controlled. Therefore, the BeNano 90 Zeta offers adjustable temperature between -10 to 110 degrees to meet various measurement requirements and allow thermal stability analysis of samples. On the BeNano software, the users have to set the target temperature of the sample and the equilibration time left for the sample to reach the target temperature. One of the intelligent functions of the software is that if you set a test temperature other than 25 degrees, you can select whether the system will maintain the current temperature at the end of measurement or return to the default 25 degrees. Now let's move on to the introduction to the BeNano software. Besides the user-friendly interface and different types of reports, the SOP, Standard Operating Procedure, is one of the highlights that allows the measurements independent of the operators. All essential parameters that the measurements require will be input accurately with the help of SOP. For the DLS measurement, the research-level software offers the intelligent evaluation and processing of signal quality to eliminate the effect of random events. Results of Z-average particle size, distribution, and PDI can be obtained by different analysis models of the software. For the ELS measurement, the software uses the algorithm of pulse to provide the zeta potential and its distribution, with several built-in analysis models corresponding to different polarity systems. Another benefit of the BeNano 90 Zeta is the enough versatility for various samples. For size measurement, there are 6 types of Cuvettes corresponding to the specific applications. The disposable plastic cuvette is commonly used within the temperature ranging from -10 to 70 degrees and only for aqueous solvents. If your sample contains organic solvents, then the glass cuvette will be a wise choice. Depending on the solvent type, sample volume, and measurement temperature, an appropriate cuvette is always available. For Zeta potential measurement, the deep cell for organic solvents and folded capillary cell for aqueous solvents are here for you. The folded capillary cell provides excellent repeatability of Zeta potential measurement. With the help of it, the instrument can provide a more uniform electric field and thereby more accurate results. It's only 4 ml thick and able to measure high concentration samples, up to 40% weight per volume. The folded capillary cell is disposable with the low cost, therefore the sample cross-contamination could be avoided. It's easy to use. When we are performing a measurement, slowly add the sample from a syringe or dropper into the folded cell. The amount of sample should just immerse the electrodes, and then insert the cell into the sample holder for Zeta potential test. For the size measurement of the BeNano 90 Zeta, there's a cuvette designed for ultra-micro volume sample called a capillary sizing cell. Extremely low sample volume down to 3 microliter is required. It can avoid large particle sedimentation, so microparticle measurement becomes possible. It has very small inner diameter, which is 1 milliliter, to avoid the effect of turbulence or convection on the signals. Another benefit of a small inner diameter is the low multiple light scattering effect that affects the size result. When you are performing a size measurement, just dip the sample and then put the cell into the supporting bracket. Adjust the height of the sizing tube until its upper end is aligned with the top of the bracket. Then, put it in the sample holder of the instrument. That's it. The sample is ready for test. So, the sample preparation becomes very easy. In addition, the capillary sizing cell is disposable with low usage cost. After a brief and quick introduction to the features and benefits of the BeNano 90 Zeta, a few key applications with this analyzer will be explained as the last part of this presentation. Lysosome is a commonly used enzyme. The simple structure and low cost make it a popular model in much current biological research. The molecular weight of lysosome is small and its scattering intensity is very weak. Therefore, measuring lysosome is always a challenge for DLS measurement. The BeNano 90 Zeta was used to measure the particle size and molecular weight of lysosome in this application. As shown in the table, the particle size was measured to be between 3 and 4 nanometers. The molecular weight of lysosome was calculated through the Markov equation using the kappa and alpha constants of lysosome. It can be seen that the calculated molecular weight of lysosome, 12.6 kilodaltons, at the concentration of 30 mg per milliliter, was very close to literature value, which is 14.4 kilodaltons of lysosome. The Z-average mean of lysosome was stable at various temperatures below 50 degrees, while they increased dramatically when temperature exceeded above 50 degrees due to a structural change caused by the denaturation of lysosome at high temperature, and consequently the generation of aggregates. As shown in the size distributions, the particle size of lysosome was initially small and had a narrow distribution at room temperature, whereas large lysosome aggregates were formed due to protein denaturation at high temperatures. In this application, the BeNano 90 Zeta was used to measure the particle sizes of two high-concentration pigment suspensions, red and yellow samples. Due to the high concentration and poor light transmittance of the sample, a capillary sizing cell with an inner diameter of 1 milliliter was used for the DLS measurement. As shown in the table, although both pigment samples were nanometer size, the yellow pigment sample had a larger particle size, but a narrower particle size distribution than the red pigment sample. The particle size difference had been discerned successfully. Studies on self-assembled Micelles can be carried out using the BeNano 90 Zeta. In this application, particle sizes of two Micelles, Twin20 and SDS, were measured. As shown in the table, on one hand, the average values of Twin20 were relatively stable upon changes in temperatures as well as concentrations. On the other hand, for SDS surfactant Micelles, the particle size highly depends on its concentration. At a concentration of 25 mg per milliliter, in addition to the formation of several nanometer-sized Micelles, large aggregates of several hundred nanometers also form. When the concentration increased to 50 mg per milliliter, the amount of large Micelle aggregates decreased significantly. In this application, the BeNano 90 Zeta was utilized to characterize the molecular weight of a PEO, polyethylene oxide, dissolved in water using SLS method. PEO aqueous solutions were prepared at different concentrations and then filtered for measurement. The scattering intensity of PEO solutions were detected at 90 degrees with various concentrations. The debye plot is then constructed by plotting and linearly fitting this value versus the concentration profiles of the suspensions. The slope of the linear regression equation is used to calculate the second virial coefficient A2, while the extrapolation of the linear regression to zero concentration uses the reciprocal of molecular weight. The deviation between the measured value and the literature value was around 10%, and the results endorse the ability of BeNano 90 Zeta for characterizing molecular weight. BSA, bovine serum albumin, is a protein purified from bovine blood. Because its spherical structure and low cost, it's a model protein widely used in industry and scientific research. BSA has very weak scattering due to its low molecular weight and is hard for light scattering measurements. In this application, the BeNano 90 Zeta obtained the particle size with DLS, the Zeta Potential with ELS, the molecular weight with SLS. As shown in the table, the Zeta Potential value of BSA sample in an aqueous solution was negative, indicating that the BSA particles were negatively charged in the current environment. Regarding the particle size, a thermal stability study was carried out. As a protein, BSA is sensitive to acid, alkali, and temperature. Its structure will change at high temperature, and its biological, physical, and chemical properties will also respond to changes, and in many cases, these changes are irreversible. As shown in this figure, particle size increased significantly when the measurement temperature reached 65 degrees or higher, indicating that BSA denatured at high temperature and formed large aggregates. In addition, we have investigated the changes of molecular weight of BSA upon the different aqueous environment. A debye plot was constructed and the slope was calculated to provide a molecular weight. According to our knowledge, when BSA was dissolved in aqueous environments, they form oligomers and aggregates. Therefore, the actual molecular weight will be larger than that of BSA monomer, which is 67 kilodaltons. And this fact was endorsed by the measurement results. In conclusion, three important properties of proteins were measured using three techniques with only one instrument. That's what the BeNano 90 Zeta can offer. Finally, here a summary is. In this talk, I have covered the fundamental concepts, optical system, features and benefits, and key applications of the BeNano 90 Zeta. But the potential of BeNano is much more than that. More technical and application notes will be released on our website and wait for your exploration. Okay, this is the end. Thanks for watching and I hope you find this video helpful. Please be sure to leave any comments or questions below and check out the Bettersize website for more detailed information on each instrument.